So I wanted to do a quick follow-up on the previous video to more properly explain how the Huffman algorithm works, the compression algorithm works, and also to show you the progress I made off screen where I kind of finished the project. So let's start by having a look at this amazing diagram I made, where you start to make a compression. You start with an input string like this. Now I just took 3 random bytes and I have them in some kind of order. So you go through your input and you count how many times each one occurs, and then you order them in a list like this. So C occurs 2 times, B occurs 9 times, and A occurs 23 times. And I have them in this list of ascending order. Then the first step of and then we view these as nodes in a tree. And then I create a new node by taking the 2 in the front of the queue, so the 2 with the lowest total weight, and I combine them to a new node. So now I've done that. C and B have been combined to a new node that has weight 11. Because 11 is less than 23, I put it in the front of the queue. In general, when there's a lot more, you put it somewhere else. So you would just put it where it fits. And then again, I take the 2 that have the lowest weight and I combine them to one node and put that node back in the queue. So now we are here. Node that is the combined node of C, B, and A with weight 34. Now this is the only node that's left, and therefore the algorithm is done. And the output, if you had tracked this binary tree that we were creating, would look like this. So remember, first I had C and B and I combined them to a new node. So you make a parent node that points to C and B as the children. And then I combined the CB node with the A node to make the CBA node that had the CB node as one child and the A as another child. So this is like the final thing, and this will tell you how to encode something. So for example, if we want to encode B, we first have to go left and then right. So we could say that left corresponds to a bit 0 and the right corresponds to a bit of 1. Then that would be encoded by the bit string 0, 1. And C correspondingly would be encoded by a bit string 0 and 0. And 1 would be encoded with just a single bit, A would be encoded with a single bit 1. So you can see the effect of this process where you keep joining the 2 nodes with the lowest weight means that those with the highest weight will be joined very late in the process, so the path to get to those is much shorter. And that means that the bit string that encodes those nodes, those bytes, will be much shorter. So to put it another way, if something occurs a lot in the string, we'll end up with a short bit string to encode that. So that makes a lot of sense because that will give you a small compressed file size. So what we can do is we can take a look at how that works here. So let's look at the compress function. So there's a lot of stuff here where I count. I make the initial counts. So let's open up this one again. So here I basically make these counts. To each byte I associate the number. Now here I create some nodes, so it's actually nodes in a graph, in a tree. Tree is also a graph, but specifically I want it to be in a binary tree. Then I insert them into a queue, priority queue, so I can always pick out the 2 with the lowest weight. And then here is the algorithm itself that generates the binary tree. So I take the element in the front of the queue, that's the one with the lowest weight. Then and I remove it. That's pop means you remove it. Then I pop one more element, which is means I get the 2 elements with the lowest weight. I make a new node, put A and B into that node. The weight of the new node is then the combined weight. And then I insert this into this bookkeeping list. And then I also insert that node into the priority queue, so I know which one to get next. You keep doing this until there's only one node left in the queue, and then that is the root node. And in our example, that would be the CBA node, be this root node. So the binary tree representation is not super convenient when you want to encode a string like this. I would rather have something that tells me that A belongs to a certain bits. It's encoded by a certain bit string. So that's why I have this codebook concept. That basically tells you for each byte in the input what is the bit string. So that's what this function does. It's not so interesting. And then I read the contents of this file that I'm trying to compress. I actually already read it up here, but I haven't refactored it, so I only read it once. I had to read the file to count how many times each byte occurred and so on. But anyway, I read it again, and then I go through each character here, each character in the content. I do a kind of a silly loop where I just loop over everything in the codebook and find the corresponding code word. And then that code word structure has the bit string, essentially. So I can go in and write all the bits to this writer struct that I made, which just allows me to write bits, single bits to a stream. Normally you can only write at the level of bytes, so you have to do some stuff to write bits. But in any case, I'm writing the bits here. Then finally, some debug statements. Ignore that. Finally, I print all the things inside the writer. I print them out to standard out. So what it looks like is if I take this one and I say I want to compress, and we can put something into the first argument is where you want to save the codebook. You need to save the codebook so you later can decompress. So let's just save it in the temporary folder. Then we can take an input here, and we can take simple input, simple.txt. It's just some file. So you see, I run it and it outputs some kind of junk. But that is the compressed representation of this file. And if we look at the file itself, let's actually do this. Then you can see it is kind of like one of those I showed, a lot of A's and B's. All right. So that is the compression part. Now the decompression part, you go in to a compressed file, you read all the bits out, and then you just follow the tree. So let's say in my compressed file, I would have a 1 as the first bit. So I go here and I see, okay, now I'm at a leaf node. That means that the first byte in the uncompressed file is an A. Then I would see a 1 again. So I go right, I see again it's A, and I see another one, again it's A. Now something more interesting happens when I see a B, because then I would see the next bit would be a 0. So I know I have to go here. It's not a leaf node, so I need to look at the next bit again. That bit then becomes a 1, so I have to go right, and I see now I'm at a leaf node. That means the next one is B. Then I see a 1, I go here, I see a 0, I go here, and a 1, I go here, and so on. Take a look at the Wikipedia page if it doesn't make sense, or try to walk through it yourself. But we also have that function up here, decompress. It loads the codebook. It reads all the files, all the bits of the file. And here you also need to do something special to get a list of bits, because normally you just read bytes. And then we go through all the bits in the reader, and every time we hit a leaf node, we stop, and at the leaf node, here we are, we see that, okay, we're at a leaf node, so the byte value must be the next byte value. Put that into the decoded string, and then we print that out. So I have made a test script here, and it runs a bunch of things. You can see it runs all the input files that are in this tests folder, and it compresses the files, decompresses the files, then it compares the input file and the decompressed file, and it also calculates the compression ratio. And there are a couple of different tests. So we can go ahead and say input, maybe like this. So you can see here we have something with 50 characters, something with 50 characters that is biased towards some of them, and so on. There's also some totally random. They come from this thing, def urandom. Sorry, I need to say how many bytes, so let's say 10. 10 bytes. You can see it just put, let's actually put them in here, and then let's put them here. And you can see it's just some weird bytes, and we can also do this kind of thing to see, just give you some junk bytes, and if I do it again, you can see it's totally different bytes. So anyway, that's totally random, totally uncorrelated, and it's every possible byte value. There is, if you want to play with it yourself, there is this gen test file that generates all the test files. So in any case, let's try to, let's do this, and let's try to run it. And you can see it ran a bunch of things, and there's only OKs, so that means, and it also says all tests passed. So it means that a test is passing if the decompressed file is the same as the input. Now the compression ratios are a bit interesting. So the optimal compression ratio should be 8. That is kind of like the maximum you can get, because it means that every single byte is represented by a single bit, and you cannot really go lower than a bit. So yeah, the maximum you can get is 8. You can see some of them are quite close, some of them are quite far, and some of them are actually not compressed at all. So this is one of those completely random things. Because it's completely random, we cannot actually do any compression. There's no reason to believe it can be compressed in any way. Especially when you have a large file, then there's essentially no compression. You can see we also have the byte count here. In this one we actually only compressed it by 3 bytes. This one we compressed it by 6 bytes. So that's it. I hope it makes a little bit of sense, and source code is in the description, and I will see you in the next one. Bye bye.